Okay, more right triangle relationships here. So we covered the basics of the right triangle, understanding sides and angles, and we introduced ourselves to the Pythagorean theorem. So now let's look at another set of operators and functions here that allow us to solve for the angles associated. You'll recall the Pythagorean theorem limited us just to calculating the sides. With the trigonometric functions, though, we can calculate the angles. And you'll notice from the relationships that the angles can be calculated from the lengths of the sides. We set up these ratios. And so if you ever wondered, really, what is a sine, cosine, tangent? The sine, cosine, tangent is really just a ratio of the sides of the triangle. So you can see from the mathematical expressions, the side opposite divided by the hypotenuse, A over C, is equal to the sine function. We call it SO. Okay, it's a part of a mnemonic. So, ka, toa. The second one, the cosine, is the ratio of the sides adjacent to the hypotenuse. And then the tangent of the angle is just the opposite over the adjacent. So by understanding those side lengths and the ratios they form one to the other, we can calculate then the sine function and then come back, and you're going to see later, using those inverse functions, calculate the angle themselves. So these trigonometric ratios then are called the sine, the cosine, and the tangent. In your text, it goes through a rather elaborate explanation of something called the Trigonometric Tables. Back when I was going to college, we're talking, 40 years ago, before the handheld calculator came out, that would only add, subtract, multiply, and divide. And then later they started adding the scientific functions to the calculator. Before these were available, you had to use these tables. And it's worth taking a look at just to familiarize yourself. The tables in your book are a little more elaborate because they let you break down the angle to smaller increments. In this case, I just pulled one off the internet here and said, okay, from your textbook, what's the cosine of 50 degrees? Well, you just look to find where the degree is, in this case 50 degrees, go down the column for cosine, and boom, now you can see that the cosine of 54 degrees is 0.5878. In looking at this number, it's interesting to note at this point that if you think of that number as a percentage, that is really giving you how much of the length of the side of the triangle makes up the triangle. In this case, it's almost 60% of the triangle. 0.5878, which is 0.59, almost 60%. So it's really, ratios are, you can relate to a percentage. So it's really like a percentage. So the inverse functions, as I promised you, the inverse functions, suppose we know the length of the sides and we need to find the angles. So the inverse functions ask the question, what is the angle whose sine, cosine, or tangent is, blah, blah, blah. So the inverse functions are the arc sine, the arc cosine, the arc tangent. We typically write them, making them look almost like an exponential here. Sine to the minus 1, sine to the minus 2, or 1, cosine, tangent to the minus 1. In telling you that we've got this relationship, much like we've seen before with the exponents. If I put sine to the minus 1 up next to a 10 to the minus 1, you've got the same sort of relationship. So the expression inverse sine of 0.74314 asks the question, what is the angle? So on your calculator, you would enter that value, hit the inverse sine, and boom, what you would get back is an angle of 48 degrees. So using the recommended calculator here, you can see kind of the keystrokes that it would take to calculate the inverse sine. So to find the inverse sine on this Casio, you would first hit the shift key, and then the second step would be hit the sine, which really activates the inverse sine. and you will get sine to the minus 1 with an open paren. Enter the sine value, in this case 0.5, and what it feeds back when you hit the equals key is 30 degrees. The interesting thing about this is as you use inverse sines and sines more and more, you'll get to where you don't even need to use your calculator. 0.5, common angle, common sine, 30 degrees, okay? So if you think about it, if you've got a triangle, and the triangle is, you already know has 90 on one side, and it has 30 on the other side, what's the last angle have to be? 60 degrees, right? Because the other two angles have to add to 90 degrees for a total of 180. So we can use trig functions and inverse functions then, along with the Pythagorean theorem, if we have to find unknown sides and angles of a triangle. So if we consider the triangle where side B is assumed to be 25 units and it forms an angle of 40 degrees, what are the sides of side A and C, and what is the angle phi? So to do this, we go back to our relationships, sine of an angle, cosine, tangent, so katoa, and look at our ratios. We are given a value, and we want to solve for a value. So in this case, we want to solve for the hypotenuse. So let's start with the cosine relationship. The cosine of the angle is equal to side B over side C. Okay, let's first manipulate the equation so that we get C on the left-hand side by itself. So the hypotenuse, C, is equal to the ratio of the side B and the cosine of the angle. Side B is 25. Cosine of 40 is almost 77. So 25 divided by 0.766 gives me a length of 32.6. Notice there are no units because there were no units associated in this problem. Okay, so what about side A? They wanted us to solve for side A and side C. So for side C, we pick, or side A, we pick one of the relationships that has an A in it. So we do the same thing. The tangent of the angle is equal to A over B, adjacent over the opposite over the adjacent. Set up the expression. Again, let's move A to the left side by itself so that the right side becomes the product of side B times the tangent of theta. So 25 tangent 40 degrees. The tangent of 40 degrees is 0.839, almost 84. So that times 25 gives me the length of side A with 0.21. In doing all these things, keep in mind, as I said, we're going to be looking at this, really applying this in terms of vectors and phasors. As we look at this, what we can really see here is side B is the x-axis of our Cartesian coordinate system. Side A is actually the y-axis. So if I take the y-axis here, side A, and slide it all the way over here and connect it on this end at the end of the hypotenuse, I have the y-axis here, the x-axis here, and I would have some radius or some resultant vector that forms the hypotenuse. So that's where we're going with this. We're using this as the basis or the fundamental for our understanding of applying this later to vectors and phasors. So now let's consider again, we have side A equal to 150 and side B equal to 300. How long are sides A and C? And what is the angle phi? So we're interested in the angle at the top, phi, and we want to solve for the hypotenuse and side A. So again, if we start with the tangent, this allows us now to solve for the angle of the angle theta. Okay, so in this case, we have 150 over 300 gives me 0.5. The inverse tangent 0.5 gives me theta of 26 degrees. I also have enough information to use the Pythagorean theorem So I can solve for the hypotenuse, and it comes out to 335. You'll notice in the next example here, I can also use the sine function, a over c, and I could have come up with that same 335 units. So you just get used to using and picking the tools that you need. Okay, as a final example, something a little different, we're going to talk about an aircraft taking off from a runway. A jet takes off at an angle of 25 degrees. If the runway from takeoff is 1,200 feet long, find the altitude of the airplane as it flies just over the end of the runway. What distance then also has the plane flown? So we're looking at the height of the A side of the triangle. That's our height at the end of the runway. But we're also looking at the vector or the length along the hypotenuse that forms the distance that the aircraft flew. So we know theta is 25. We know the adjacent side is 1,200 feet. So side B here, that really forms our runway. So if we take the function tangent theta equals the opposite over the adjacent, move our terms around so that we're calculating the opposite side A, opposite side theta, we can plug in our values. The tangent of 25 degrees times the length, 1,200 feet of the runway, gives me now a height of 560 feet off the end of the runway. The hypotenuse of the right triangle is the distance then that the airplane flew. Then if we use the equation cosine theta is equal to the adjacent over the hypotenuse, we can solve for the length of the hypotenuse. So the hypotenuse is equal to adjacent over cosine theta, 1,200 feet by cosine 25 degrees, and we get a length of the hypotenuse, 1,320 feet. So getting used to these manipulations is going to help us later when we start doing our AC analysis and we go back to what I told you about the real and the imaginary resistance, reactance, impedance. Okay, so we will see all of this. So we skipped a chapter 15, and moved on to 16 here so that we could get these foundations taken care of.